In the previous video, when we studied the questions governing a non-relativistic perfect fluid, which is moving free from external forces, we saw that it was very natural to construct this tensor and this 4x4 tensor, although this is only this 3x3 part here is the Newtonian stress energy tensor. Okay, the equations have a very natural four-dimensional form. So one could indeed look at this T mu nu as the non-relativistic limit of a fully relativistic T mu nu. And the usefulness of this T mu nu is that its equations of motion would follow from this equation, okay, which is typically called the conservation law of the energy momentum tensor. Okay, although we will have to be very careful with this conservation law. So the idea, okay, is that there should be some generalization of this tensor such that in the non-relativistic limit gives you this. One way of finding this tensor would be to first write this non-relativistic tensor in a frame which is co-moving with the fluid. So the velocities are 0. Okay, in this co-moving frame, u mu, which is the velocity, so these are in this case the derivatives of the x mu's of each fluid element with respect to the proper time. In this co-moving reference system, this is 1 and 0. If the velocities are 0, you know that you are moving in the same reference frame, and that by definition the coordinate time of that co-moving reference frame is equal to the proper time. Okay, we are here working in units of c equal to 1. Okay, so in this frame in which there is no motion, this tensor takes the form rho and then p, and the rest of the components are 0. Now if we write this tensor in a relativistic form, because they should coincide, this is, if you want, the non-relativistic tensor for v equals 0 and the fully relativistic tensor in this co-moving frame, they should coincide. So if I manage to write this in a fully relativistic form, then I will get the result that I want. So this form is just this. Okay, so this is minus p eta mu nu, so that for components ij, this is minus delta ij, minus and minus is plus. This gives me these 3 p's, but it also gives me minus p eta 0 0. Okay, so I can remove this p by multiplying p with u mu and u nu, because here in this frame u mu and u nu only have 0 component, which is 1. So this minus p and this p are 0, and then rho only appears in the 0 0 component. Okay, so in this particular system, okay, this form reduces to this. And now, since all these objects are covariant, then if I perform like a Poincaré transformation, I go to any other frame, then I should get the correct result. And this is the form of the energy momentum tensor of a perfect fluid relativistic perfect fluid. Okay, let me put it here in a box, because it is an important result that extends its validity to more general cases. Okay, probably with the replacement of the special relativistic metric by a more general metric, as you can expect. Okay, the next thing would be to study, if you want a non-relativistic limit, but for small speeds, and see that you find this expression here, in which the velocities are not exactly zero. Okay, this we can do as an exercise, and after that exercise you can also try to study what is the relativistic version of the conservation of what are the implications, which continuity equations, and what is the relativistic version of the Euler equation. We are not going to do these calculations in full detail. There is only one thing that is important for us, which is what is the component T00 for a perfect fluid. So let me just compute it. So I have minus T00, you have U0 P plus rho. This should be the energy density, right? And minus P. Now I need to use result. As you know, the square of the force velocity or the value of the force velocity is just 1 by definition. Okay, let me remind you that this is just dx0 ds square minus dxi ds squared, and okay, the fact that this is equal to 1 is because you can take the ds squared to this side. Okay, minus dxi. So from this fact, okay, this is an explanation. Okay, so let me say that this is u mu, and this is equal to 1. Now this is dxi over ds, but let me write this as dxi dx0 ds, which is vi u0 for each of these ui's. So what I have is u0 that is squared, that can be taken as common factor, 1 minus vi, and this is equal to 1. From this I get that u0 squared is 1 divided by 1 minus v squared, and u0 is 1 divided by the square root of 1 minus v squared, always in units of c equal to 1. So if I write this here, okay, first I take common factor u0 over everything, and I have rho plus p, and then I have 1 minus 1 divided by u0 square. This is the only thing I get when I take u0 as a common factor. Now u0 is given by this expression, so if you come here you find that this is v square. Okay, so I get u0 and then rho plus p and v square. Okay, this quantity is what should play the role of energy density, and as you see, it depends on p. Okay, so the main lesson is that in a relativistic fluid, perfect fluid, the pressure contributes to the energy density. If, as we will see, energy density is what really gravitates, what creates a gravitational field, or one of the sources of gravitational field, this means that pressure will contribute to the gravitational field as much as the energy density. So if I compress some matter and then I increase the pressure, In general, I increase the gravity, but the pressure typically opposes to this compression. And however, here at some point, although the pressure opposes to the compression, it will also increase the gravitational field when it grows because it increases the energy density, so it will tend to increase the compression. So there is a delicate equilibrium between what the pressure can do to oppose the compression and the fact that it creates more gravitational field. And this is a radical difference between the Newtonian gravitational field and the relativistic gravitational field that leads to gravitational collapse that cannot happen in Newtonian physics. The very last thing that we need to see about relativistic fluids are the typical equations of a state that one finds. Remember that these are relations between pressure and uh, mass density. Okay, and the ones that we will typically find are of this form. So this will be some constant. This is not the same omega that we use there. Okay, but it's just a constant of proportionality between pressure and density. So remember, for zero pressure, we have incoherent matter. This is an equation of a state, or dust, as we called it. If P is equal to 1/3 of the energy density, to have hot relativistic matter. Okay, such as, for instance, radiation. And another particularly interesting case is the case in which pressure is minus the mass density, and this is precisely the behavior of what is called nowadays dark energy. Dark energy. These are the cases that you probably should remember.